Hello. In this video we begin Chapter 14, our unit on acid-base chemistry. As you can see from the outline, it's a pretty long unit, so let's go ahead and get started. In this section I'd like to talk about the nature of acids and bases, and you may recall from our first year of chemistry that there are a number of acid-base theories or models that we can use to understand the properties of acids and bases. And yes, they're named after dead white European males. First one is named after Arrhenius, whose name you might recall from Chapter 12, the same Arrhenius as the Arrhenius rate law. Arrhenius studied many solutions of acids and bases, and he realized that acids have one thing in common, and that is, according to Arrhenius, an acid is a substance that increases the concentration of the hydronium ion, or H+, in aqueous solution. Now, you may recall that H+, a naked proton, is too unstable to exist in solution. When it is formed from an acid, it immediately jumps onto a water molecule to form H3O+, the hydronium ion. Nonetheless, we can always use H+ as a convenient abbreviation for the hydronium ion. A base, according to the Arrhenius definition, is a substance that increases the concentration of hydroxide in aqueous solution. You'll recall that H+ and OH- are complementary, and we'll see why in a little bit. The limitation of the Arrhenius model is that it only applies to aqueous solutions. Still, that's a pretty broad definition. A more general theory or model is the Bronsted-Lowry theory. And according to Bronsted and Lowry, an acid is a proton donor. So if in a chemical reaction a reactant gives away H+ to another reactant, it is the acid. The base, on the other hand, is the substance that accepts or receives H+. The limitation of this model is that it only applies to proton transfer reactions. Still, these two models will encompass the great majority of acid-base reactions we'll consider. The third model, the Lewis model, we'll talk about towards the end of the unit. Let's consider a general reaction for the ionization of an acid in water. Here, HA reacts with water in an equilibrium to form the hydronium ion, H3O+, plus A-. What's left after HA has given away H+ to water. Let's look at some Lewis structures to try to understand this. I'll show HA here. Let's just pretend it looks like that. Reacting with a water molecule with two lone pairs. In the equilibrium, water accepts a proton from HA to form the hydronium ion, and A- is left in solution. Let's do some definitions. The acid is the proton donor, the reactant that gives away H+. The base is the proton acceptor, the reactant that receives H+. We have names for the products too, you might recall. The conjugate acid is defined as what the base becomes after it has accepted H+. The conjugate base is defined what's left of the acid after it donates H+. The conjugate acid and conjugate base are always on the product side, as written, so let's label these. In this reaction, clearly HA is the acid, water is the base. Hydronium is what the base, water, became after accepting H+, therefore it is the conjugate acid. A- is clearly what's left of the acid after it's given away H+, so A- is the conjugate base. So a skill is look at a chemical equation to represent a proton transfer reaction, that is a Bronsted-Lowry acid-base reaction, and label the four components. Let's think about this equilibrium in a bit more detail. Okay? Here's our equilibrium, HA plus water, in equilibrium with the hydronium ion and A-. We can think of this acid-base ionization equilibrium as a competition between two bases for the proton. There are two bases in this reaction, water and A-. Think of them as fighting over H+. Who gets H+? Well, if water is a stronger base than A-, meaning if water has a greater tendency to accept the proton than A-, that means the equilibrium will lie towards the products. Okay? If water is the stronger base, then it will preferentially take the proton, and it will exist primarily as the hydronium ion. This means we favor the products. In this case, we would say that HA is a strong acid. It is fully ionized. On the other hand, if A- is a stronger base than water, if it preferentially takes the proton, then that means it's going to exist primarily as HA, the unionized acid. In this case, the equilibrium favors the reactants. We would say HA is a weak acid, which is only partly ionized. I'll explain these in more detail in a couple of minutes. So, one way you can think of it as whichever is the stronger base, that one pushes the equilibrium toward the opposite side. Okay? And we can write an equilibrium expression for our generalized acid ionization reaction, which is as follows. Ka is equal to the product of the hydronium ion concentration and the conjugate base concentration over the concentration of unionized acid. And once again, we can always abbreviate the hydronium ion as just H+. So let's write a balanced equation to represent the ionization of perchloric acid and write the corresponding Ka expression. For perchloric acid, I'll write HClO4+, reacting with water in equilibrium with the hydronium ion plus the conjugate base, which is simply the acid minus H+, or ClO4-. Ka for perchloric acid is the product of the hydronium ion concentration times the perchlorate concentration divided by the concentration of unionized perchlorate, or if you prefer, you can simply do H+, ClO4- over HClO4. So for each of these ionization reactions, label the acid, the base, the conjugate base, and the conjugate acid. So your job is to look at the formulas of the reactants and products and figure out who's giving away H+, who's accepting H+, and label them from there. So if you'd like to pause the video for a minute and complete these, go right ahead. So in the first problem, we have HONH3+, the hydroxyl ammonium ion, reacting with water to form HONH2 plus the hydronium ion. Clearly, the hydroxyl ammonium ion is giving away the proton. Water is accepting the proton. HONH2 is what's left of the acid after giving away a proton. It's the conjugate base. Hydronium is the conjugate acid. Oh, interesting. We have a hydrated metal cation, hexa-aquo-aluminum 3+, reacting with water to form the hydronium ion, and penta-aquo-aluminum hydroxide. Clearly, the aluminum complex is giving away the proton, and water is accepting it. Again, hydronium is what the base becomes after accepting the proton, and this is what's left after the acid gives away a proton. In the third one, we don't have water involved at all. We have these molecules whose formulas may not mean anything to you, but that's okay because you can still look at it and figure out whatever HOCl is, it's the one that's giving away the proton. C6H5NH2, I don't care. It's clearly accepting the proton, so it's the base. OCl- is what's left of the acid after it's given away H+, and C6H5NH3+ is clearly what the base has become after accepting a proton. Okay, now let's talk about acid strength. Is acid strength related to concentration? To say an acid is strong, does that mean it has a high molarity? No, it does not. Those are two completely separate issues. A strong acid is defined as one in which the ionization equilibrium lies far to the right. Ha plus H2O, here I'll use a single arrow pointing towards the right to indicate complete ionization of Ha. Okay? Effectively, all of Ha is ionized to form H++ A-. Okay? At equilibrium, the concentration of remaining unionized strong acid is effectively 0, so Ka is too large to measure. We don't even measure Ka. The hydrogen ion concentration at equilibrium is effectively equal to the initial concentration of the acid. That will become important later in the unit when we talk about calculating the pH of strong acids. And this is important because Ha is fully ionized, the conjugate base A- has a low affinity for the proton, meaning that A- is a weaker base than water. Water preferentially accepts the proton, so it is a stronger base than the conjugate base of a strong acid. Here are some common strong acids, and yes, I want you to memorize them. You should know the names and formulas of the 6 common strong acids. There are the hydrohalic acids, hydrochloric, hydrobromic, hydroiodic. Notice hydrofluoric acid is not a strong acid. Nitric acid is a strong acid. Perchloric acid is a strong acid, as is sulfuric. However, you'll recall that sulfuric acid is a diprotic acid. Only the first ionization is strong, the second is weak. We'll deal with that later in the unit. On the other hand, for a weak acid ionization, the ionization equilibrium lies far to the left, meaning that the reactants are favored. Okay? At equilibrium, very little of the acid is ionized to form H++ A-. The remaining equilibrium concentration of unionized acid is very close to the initial concentration of acid, so Ka is very small. Normally, the equilibrium constant for weak acid ionization is 10 to the negative second or smaller. The remaining the equilibrium concentration of H+ is much less than the initial concentration of acid. Now, in contrast to a strong acid, the conjugate base has a very high affinity for the proton. Okay? Remember, it's a competition for H+. If it is a weak acid, the equilibrium lies towards the reactants. That means A- has a greater tendency to accept H+, so it exists primarily as HA. And this is important. The conjugate base of a weak acid is a stronger base than water. We'll be coming back to that many times this unit. Ooh, here's a really interesting problem. I've got a proton transfer reaction here. Hypochlorous acid plus acetate forms hypochlorite plus acetic acid. The equilibrium constant for this reaction is 1.9 times 10 to the negative third. Can I use that value to determine which is the stronger acid, acetic acid or hypochlorous acid, and why? Well, if K is small, if K is less than 1, that means in this case the reactants are favored, okay, which must mean that acetic acid has a greater tendency to give away H+ than hypochlorous acid, HCl. So we would predict that acetic acid is the stronger acid. Okay? Another way to think of this is that because the equilibrium lies towards the reactants, acetic acid must be pushing the equilibrium towards the left. Here are some common weak acids. Please do not memorize these. You will always have a table of Ka values, so you can always look up and see whether it's a weak acid or not. Another way to think of it is, if it's not one of these 6 common strong acids whose names and formulas I asked you to memorize, it's a weak acid. Now, the last one, acetic acid, is important, and it is an example of a category of acids called carboxylic acids, which are organic acids that have the carboxyl group, which looks like this. If you have taken biology, you will recognize this. If you have not, you will, and it's important to notice that whatever else is in the molecule, it's only a hydrogen on the carboxyl group that comes off as H+. That's the only acidic proton in the molecule. Here's a table of Ka values for common weak acids. You will always have these, and you can see these range dramatically. The hydrogen sulfate anion has a Ka value of 1.2 times 10 to the negative second, whereas hypoiodous acid has a Ka value of 2.0 times 10 to the negative 11th. Oh, what is that? A billion orders of magnitude? Yeah, they can vary dramatically. Now, let's move on. Water, you may recall, has an unusual property. It is what we call amphoteric. What does that word amphoteric mean? It means it can behave as both an acid and as a base. Okay? And here is the equation for the self-ionization of water. Water, under normal conditions, undergoes a process called self-ionization, in which 2 moles of liquid water are in equilibrium with 1 mole of the hydronium ion and 1 mole of the hydroxide ion. Let's see what that looks like. So here's a water molecule, and here's a water molecule on the reactant side, and they are in equilibrium with a hydronium ion, positive charge, and a hydroxide ion with a negative charge. What we can clearly see here is that one water molecule has behaved as an acid by giving away H+ to the other. The other has behaved as a base by gaining H+ from the first one. Okay, oops. Okay. Here is the equilibrium expression for the autoionization of water. K, which you'll recall we label as Kw for the self-ionization of water, is equal to the product of the concentrations of the hydronium ion and the hydroxide ion, or H+ times OH-. We leave out the liquid water on the reactant side because it is the solvent and its concentration is so large as to be effectively constant. We find via experiment that in neutral water at 25 degrees Celsius, the concentrations of the hydronium ion and hydroxide ion, first of all, are equal to each other, which they must be because they're produced in a 1-to-1 ratio, and they're equal to 1.0 times 10 to the negative 7th molar. Therefore, the numerical value of Kw at 25 degrees Celsius is simply the product of these concentrations, or 1.0 times 10 to the negative 14th molar. A skill, then, is given either concentration, first, tell whether the solution is acidic, basic, or neutral, and second, calculate the other. Now, it seems to me that this stuff belongs in 14.3, so I'm going to talk about it more there. Now, I can talk about this, though. In an acidic solution, the concentration of the hydrogen ion is greater than that of neutral water, so that's greater than 1.0 times 10 to the negative 7th molar, But because the concentrations of hydroxide and of the hydrogen ion and the hydroxide ion are inversely proportional, if in an acidic solution the concentration of hydrogen ion is greater than 1.0 times 10 to the negative 7th, the concentration of hydroxide must be less than 1.0 times 10 to the negative 7th molar. Conversely, in a basic solution, the concentration of the hydrogen ion must be less than 1.0 times 10 to the negative 7th molar, and the concentration of hydroxide must be greater than 1.0 times 10 to the negative 7th molar. If this is confusing, just remember the Arrhenius definition. According to Arrhenius, the hydrogen ion is what makes something acidic. Therefore, in an acidic solution, its concentration will be greater than that of neutral water. Also, according to Arrhenius, in a basic solution, the hydroxide ion concentration is greater than that of neutral water. In a neutral solution, the concentration of the two ions are equal to each other, and they are both equal to 1.0 times 10 to the negative 7th molar. That's our definition of a neutral solution. So let's finish up with a few problems. Indicate which acid is stronger and provide an explanation. HCl or HNO2? Well, again, I told you that you need to memorize the names and formulas of the common strong acids. Hydrochloric acid is one of those, so HCl is stronger because it's a strong acid. Water or HF? Well, if we go back and look at the table of Ka values, we will see that HF has a value on the order of 10 to the negative 4th for Ka. That's much greater than water. In fact, any of the weak acids on the table of weak acid ionization constants is a stronger acid than water. For hypochlorous acid or hydrocyanic acid, you can't tell by looking at it. You basically have to go back and look. So let's scroll back and look at those Ka values. Hydrocyanic acid has a value of 6.2 times 10 to the negative 10th. Hypochlorous acid has a value of 3.5 times 10 to the negative 8th. That looks to me like hypochlorous acid is going to be the stronger acid. Finally, a slightly more complicated question is, indicate which base is stronger and provide an explanation. Well, now we have to recall the following. This is very important. The conjugate base of a strong acid is a weaker base than water. The conjugate base of a weak acid is a stronger base than water. So if I look at the first two, I see clearly that chloride is the conjugate base of hydrochloric acid, which is a strong acid. Therefore, it is effectively non-basic. It has no affinity for the proton whatsoever. Therefore, water is the stronger base. On the other hand, the cyanide anion, Cn-, is the conjugate base of the weak acid, hydrocyanic acid, and a general rule is that the conjugate base of a weak acid is a stronger base than water. It has a greater affinity for the proton, therefore cyanide is the stronger base. Acetate versus hypobromite. They are both conjugate bases of weak acids, acetic acid and hypobromous acid respectively. The stronger base is the one with the greater affinity for H+, therefore it will be the conjugate base of the weaker acid. Which of these two is weaker? Well, if I go back and look at acetic acid and hypobromous acid, I will see that hypobromous acid clearly is a weaker acid than acetic acid by about 4 orders of magnitude. Because hypobromous acid is the weaker acid, its conjugate base will be stronger, so I will choose hypobromite as the stronger base. And I believe that's my last slide. Yes, it is. So in the next video, we will talk about the pH scale. See you then.